and this would be at the other end of the
Exactly.
tank. They also made so safe you could literally shoot a gun at them.
Both is important because you want
I
to
can see them here.
shorten the filling time. Yeah, exactly.
Yes.
But not only the German one, yes.
How do you make a valve sitting on a hydrogen tank absolutely safe? What specs do you need to know when choosing an on-tank valve? Today, we're going to look at on-tank valves. Welcome to Highfinder Tech Talks. My name is Steven, and today I'm joined by a mechanical engineer who has been an expert in super high pressure areas, 6,000 bar upwards, and has, I think, recently has, I would say, lowered himself into the pressures we use in the hydrogen economy. He is a very seasoned man in that field, works at Potthoff currently as Director of Technology for the hydrogen portfolio. Welcome, Burkhard Hahoff.
Hi, Steven. Thank you for having me here.
Burkhard, it's great that you're here and you didn't come alone. You brought something with you. What is this?
Yeah, this is a so-called on-tank valve for 700 bar hydrogen system. And we have released that now after passing the certification.
Okay, so this one's on the market, is certified, and works. So let's delve right into this. Where do we find that? And I see you brought a bit of a diagram here.
We have a good picture here to show the positioning of all the components in the system. You see the long tanks here,
yes.
which are placed here in the frame.
These are, okay, we have 4 tanks here.
Yeah, we have 4 tanks.
And
it
then
can be also more or less, but nevertheless, you normally have multiple tanks. And we have the on-tank valve sitting here on the top of the tank. And the opposite of the tank, we place a so-called end-plug TPRD, which is also shown here.
Yeah. So this is the one end, and this would be at the other end of the tank.
Exactly. You must plug a tank on both sides.
On both sides, okay.
That's the reason.
It's like a German sausage has 2 ends. Yeah.
Yeah, exactly.
Yes.
But not only the German one. Yes.
And you have a bit of a simulation here as well to show that.
Yes, exactly. We have here placed all the components we have in the system that are the on-tank valves, end-plug TPRDs, the parallel charging unit, and also the high pressure regulation unit.
Okay, so these are the on-tank valves here.
Yes, exactly. And the system is fueled from this side.
All right, okay.
And if we look how it happens, you see how the fuel is coming into parallel charging those cylinders. The cylinders or tanks here are slightly without any color to make it more visible.
Yes.
But nevertheless, you must imagine here could also be a bigger tank or more tanks.
Okay, so this is for illustration, yes.
Yeah, this is for visualization. And what you see here, once again, how is it is fueled. Yeah. And the opposite way to go to the fuel cell is also interesting. There it's going through the high pressure regulation unit, which gives you a pressure what the fuel cell needs. So you have 700 bar in the tank and need 10 bar, for example, for fuel cell, or 15, 20 bar for PFI combustion engine. Then this high pressure regulation unit regulates the pressure down. From the pressure of what is in the tank.
Okay, so that's this part. Okay. I think we need to talk about all this a little bit later. Let's focus on the actual on-tank valve. And so this lets out the same pressure that's inside the tank directly out. Can you take us a little bit deeper? How does this exactly work then?
Yes. I have here an exploited view on the on-tank valve itself. So you see here the single components. So in principle, this is a function block of different features.
Okay.
Yeah? So we have the aluminum body for sure.
That's this blue part.
That's the blue part. Yes, exactly. And then we have the solenoid.
Yes.
We have the manual and the bleed valve. We have the in and out. We have the so-called TPRD. Yeah, and we have also inside the tank. The tank is ending here, or the tank connection is here. We have the sealing, and we have a temperature sensor, and nozzles, and others.
Okay, so this is the temperature sensor, this little one here, and this is where the hydrogen will go into the tank.
Exactly.
And what is this one?
That is going out.
Oh, okay. So you have a different one for coming in and another one for coming out. Okay. All right. Okay.
Yeah. Important is we have a temperature issue with hydrogen. So hydrogen is behaving the opposite to other gases. So if hydrogen expands, it gets hot. Okay. So that means we have a Type 4 tank. That's a carbon fiber and a plastic matrix. And that means you could damage if it gets too hot during the expansion process. There could be a damage at the cylinder. And therefore, we have here a special nozzle which divides the stream in different numbers of streams.
Okay, I think we can see that here. It's also very nicely done here. Okay, so that's your way of solving that problem, taking that, spreading that a little bit.
Exactly. Exactly.
And so I know from way back that actually, I mean, we can't actually look inside it now here, but just from a process perspective, can you take us deeper? What flows are we seeing here?
I mean, there we would like to go to the pneumatic plan of the system, so the so-called PID.
PID, okay.
You see here the tank bottle and different colors for the different flows.
All right.
We have at the one side the in and out, which is done via one pipe, going through a 10 micron mesh filter, going through the manual valve. So the manual and bleed valve are more or less for a repair or for maintenance issues.
Okay. So those are these ones.
Yeah, exactly. You can close there, or you can open the passes.
Understood.
And then it's going here through the check valve and then to the nozzle into the tank.
Okay, so that is the fuel refueling now. That goes in here.
Exactly.
And this is a valve in one direction.
Yes, exactly. It closes if it comes out, but because the flow should be in one direction.
Exactly.
It's a check valve. Then we have if the fuel cell needs the hydrogen, we have again a filter. There are two filters necessary because in front of every valve there should be a filter because there could be some dirt. In the gas, should not be, but could be. So you want to be absolutely safe. You want to be robust in the system, and that means you need a filter there. And there's a filter, then the excess flow valve, and then the solenoid valve. The solenoid valve is the main block. It opens and closes the stream and leads to a controlled opening of the stream itself.
That's this, right?
Exactly. And the signal comes from the control unit. And,
right here.
It opens there.
So this is the solenoid.
Exactly.
Which goes directly to the control system.
It's in our case, it's a combined connection. So this connection is also used for the temperature measurement. So, but you are right. The ECU is controlling the solenoid, and the connection is there.
Okay. Cool. So
then we have another pass. This is a yellow one, and this is going to the TPRD. The TPRD is a safety feature, thermal pressure relief device, called out, and this only is in function if the temperature is getting too hot.
Okay, so this is basically, it has direct access to the tank and will let out the content.
Exactly. So the reason for that is the possibility of fire. Yes. So you want to be safe even if the temperature is going higher. Yes. So it's adjusted at 110 degrees, and if the temperature in the system exceeds over this 110 degrees, it opens and it opens to a vent so that the hydrogen can flow to a safe point
that's the
on the street or above the roof. So this is very important. Also the defueling time or the emptying time of the tanks is very important.
So that means, and would it empty almost faster than you could refuel it, or just about that?
No, there are certain geometric
restrictions
in the construction. So, as I said, as fast as possible, but that should not be too fast. You have other
issues,
challenges.
Okay. Just to round this up, what is this part here? What are these?
That is another port which you could use. For example, if you want to adapt a pressure sensor, you can use this port. You can use also as a live port because the temperature thermal pressure relief device can also be used in other areas of the system. And you could use this port for doing this. Or you can, if you don't need it, you can only plug it.
Okay. Okay. So this is live pod for measuring temperature. Why? Can you say again just why that is so important to measure the temperature in the tank?
This live pod is not measuring for temperature. The live pod is measuring, or you could apply a pressure sensor if needed.
Pressure sensor. Okay.
Temperature is so important because of the danger to getting too hot.
Yes.
Some customers are using the temperature measurement at the on-tank valve. Others at the end plug, TPID, so opposite of the tank, because it's a little bit more stable to measure their temperature. Yeah. So this has some advantages, and we have also solutions for doing that because more and more customers are demanding it. Yes, because this temperature sensor is near at the outcome throttle.
Yes.
And that means there could be a deviation between the real temperatures and the measured temperature.
Okay.
And you want to avoid that. That's clear.
So now we've seen the inside works of this, the PID. Wow. Can you give us some guidance? What specs do we typically talk about when we want to go out shopping for a contact valve?
So it's not so easy to go out shopping. I have here only a rough overview about the regulation. It depends a little bit in which market you are delivering. For the stationary market, we have the so-called MOTVs, which we also could provide.
Yeah.
They have a different regulation system. Marine has, again, a different system. And for planes or for... it's also, different. But we are talking about mobile applications here. This is on-tank valve.
Yeah.
And there I have put some regulations here into the table. Yes, you see here material regulations, which are calling out for the material specs.
Yes.
And especially are testing, or they describe the tests for mechanical properties of the material under hydrogen atmosphere. There is a CHMC1 in the US, there's the ISO 11114, and there are companies who create the standards for this, for testing out this, for example, the TÜV.
TÜV did one. Okay. That's not.
And if you look on the component side, at present we have the HGV 3.1, the R134, and also it's released 1 month ago or 2 months ago. That's the ISO 19887, which is putting all this stuff together. Because at present we have here the challenge that we have regional norms. What you see is not all. In China, it's the GBT. In Korea, there's another one, and so on and so on. And you have to, or the challenge at present is to have, or we want to have one norm for all the regions.
Okay. So basically you're saying when you're going out shopping, the first thing is to know what application, what norm applies to my area. So if I'm running a truck in China, it's going to be different than when I'm running a truck in France, for instance.
You have to check according different
norms,
regulations.
Okay. Yeah. What other things? I mean, are we talking? What about the pressure?
For sure, the pressure is very important. So it's a difference between 700 bar and 350 bar or 500 bar in stationary applications. So this is very relevant for the application you want to have.
When looking through your norm sheet, and forgive me for doing so, I saw this one kV value. This is it's right here. We have the spec sheet right here. Is that also one of the key things to look out for?
The kV value is, at least if you look at the definition, at least a definition of the flow capacity component, and it makes components comparable. If you have our on-tank valve or another on-tank valve with a kV value, you can compare those for the flow capacity. And why is the flow capacity so important? Because it describes how fast you can fill through the on-tank valve, the tank, and how fast you can empty the tank. So we have two values. One is for the filling pass, and the other is for the pass to the engine. And both is important because you want to shorten the filling time. So if you speak about filling time, you don't need to go drink a coffee with the filling time. So it's not so long. It's a few minutes, depends on the tank size, but it's relevant and it's a unique selling point if you are good there. As higher the value is, as better we are.
Ah, yeah. So that means here we have 0.28, for example, and that is obviously faster or more material going through than during the deep-filling. And so, okay.
And you see also the ZV value. Yeah, the Americans are measuring in gallons.
Right.
So the definition is a little bit different, but there's a certain calculation factor between that, 1.16 or 1.18. I don't know exactly, but yeah.
So that means, obviously pressure, then the rate of flow which can go through this.
Yes.
And of course, this thing has to be in the right norm.
Exactly, and it has it has to be very small. Yes, because you want to make the tanks as big as possible.
Right.
And if you make the on-tank valve in height very small, we have here 38 millimeter.
Oh, right.
That's not much.
Yeah.
Actually,
I do remember when we worked on a project once. We had a certain size. Actually, we could accommodate. I mean, vehicles have a certain breadth. And if you want to lie the tank, the on-tank valve, you're really fighting for every millimeter.
Yeah.
Because I think, and I don't know whether this is still the case, the tanks also can get longer and shorter depending on...
Only a few millimeters, but nevertheless...
You have to accommodate for that.
Yeah, sure.
Okay, so you guys with 38 millimeters, you say?
Yeah.
Okay, cool. Well...
Mm-hmm. Yeah, and the main points are efficiency, reliability, and safety. Safety is the main point.
So let's talk that a little bit. How do you make this thing safe?
Yeah, it depends a little bit what feature you are looking on. There are different features. So, for example, you want to avoid blocking the valves. We saw that there are filters in it. It's a safety issue. If a valve blocks, then you have a problem.
Okay.
Yes. But the main point is for safety also this thermal pressure relief device. I have brought a picture with me.
Okay.
Yes, and what you see here is a mechanism.
So this is this.
Exactly.
Yeah, this is the exploded version of that.
Better than me.
Yeah, I think you explained this because I was immediately asking when you came.
That's fine.
Yeah.
And this is a construction with a glass bulb.
Yes.
I have brought one with me.
Okay.
Yeah.
Okay, so that's how that looks. Yeah.
So in principle, there is a liquid in it which has a vaporization or trigger temperature, which is at the temperature you need to burst this glass bulb. So this is in this case 110 degree.
Okay.
Yeah? And if it bursts, the mechanism is working and leading the vent path free for evacuation of the tanks.
All right.
In principle, there are two constructions. Yes, this is a glass bulb construction. It has some advantages for example, accuracy of it.
Yeah.
But there are also other constructions like fused metal. TPRDs, which are working with an alloy, which has this trigger temperature. So there are also challenges, but also disadvantages. So I'm showing here this kind of device.
Okay, so that brings in that safety when the temperature goes higher, bursts and lets out the gas through
this port here.
Yeah. Okay, so this is the out. TP. You can see the TPRD vent is written on it. Actually.
Exactly.
Okay, perfect. And you use this technology, but you're also open to working with other technologies
are also available.
Yeah. And just one more thing. I know that especially you have worked with like super high pressures, and I guess that there's also some work that some of your experience that needs to go into that to making this safe.
Exactly, and out of our knowledge, we are also building our test machines ourselves.
All right. Okay.
I've brought here with me one picture of a test machine which we have in our innovation lab.
Yes.
And here you see a test machine with two chambers for testing for high pressure. So you can put here different cycles. So you can make static tests, you can make burst tests, but also cycling.
Yeah.
Hydraulic cycling at this point. And you see here in this graph different profiles. For example, you can supply a sinus curve, a pressure curve, so going in 1 second 2 times up to 1,000 bar, or from 50 to 1,000 or higher, as you want, or as the regulation wants to see it.
Will we actually in reality see these kind of fluctuations in a tank?
No. If you compare that with my former technology in diesel area,
Yeah.
it's quasi-static.
Yeah.
Yes, but
Okay.
nevertheless,
But they
from
make-
this results, you can make your lifetime calculations.
Oh, yeah, lifetime calculations. Okay, obviously, yeah. And because I also read a little bit about the material, the tanks. I know the tanks they are so they're also made so safe you could literally shoot a gun at them and still work.
That's true, but on the other side, you have safety factors. The safety factors should be as high as possible, and for sure, also we have to talk about cost efficiency.
Yeah.
So you cannot make such walls. Yeah, you have to find compromises,
Okay.
and that testing helps you to find this cost and robustness compromise.
Okay. Okay. So speaking of cost, robustness, safety, can you give us a little bit of an outlook? Yeah. So I know that this is a cost factor in the entire setup. In fact, the whole hydrogen supply chain is something that is always important.
Yeah.
Can you give us a bit of an outlook? Where is this going? What are you seeing? What trends and so on?
Okay. I mean, cost is another point, but it's a point which hurts
Yeah.
as an end consumer, so it's important. But if you look at present on the market, we look on different, we touch briefly the regulations,
Yes.
to put that together in one regulation. So that would help us a lot, but also technical points, make it more robust. For example, for temperatures which are going lower than the demand
Yeah.
minus 40 degrees at present. So the OEMs have measured in systems also temperatures up to minus 60 degrees.
All right.
It's at present not reflected, but we have created our own test programs for that to be also safe.
Okay.
Yeah? And this is really a challenge for the ceilings, because the ceilings, they have a big spread from minus to plus temperature.
Right.
And there it gets challenging. Yeah.
Well, obviously, I think if you have the right test equipment, then, of course, you have to.
It helps,
sort-
yes. Yeah.
So that means you're seeing even lower temperatures that you guys will cover. And I guess probably also if there's a simplification of the norms, then the costs
Exactly.
can also reduce.
So what will come in the future is for sure changes in architecture. Is it really sensible to put on every tank such a complex device? That question some people ask. To combine functions, to make it simpler but more robust. That's the way we are going.
Okay, and Popopotov is obviously building that way as well.
Sure.
Yes,
Yeah.
perfect. Well, Burkhard, I think we've really gone through this thing in a very short time. Thank you very much for coming out and bringing all your experience with it, especially bringing this buddy with. If you want to find components like these and get in touch with people that do this, then there's more on highfinder.com, obviously, where you'll find things from Popopotov, more products along that whole hydrogen chain. We took this one as a sample for once. Thank you very much for watching. Nevertheless, thank you, Burkhard, for explaining all this. And
Thank you for having me here.
yes, and if you like this, do follow our channel or give us a like. And there's many more videos that you can watch. And Burkhard, I'll be giving you a coffee after this, and maybe we can do another one on a little more of the whole pressure devices.
Yeah, you're welcome.
Thank you very much. Have a good day. Thank you.
Thank you.